Welcome to the video lecture on dividing polynomials. We're going to start off today with reviewing how to do long division and synthetic division of polynomials. So let's take a look at this first example. This is a long division problem, and we're going to do the exact same long division algorithm that you learned in elementary school when you learned to divide numbers. However, we're going to do it with x's as well as numbers. So the first thing you want to make sure of is that the polynomial that's listed under your division bar has every power accounted for, and it should be in descending order. So we've got our x cubed term first, then our x squared, then our x term, and then our constant. So every term is accounted for, and it's going in decreasing order, which is exactly what we want. Once it is set up correctly, we're going to take our divisor, which is this quantity on the outside, and we're going to think about x times what would give me 12x cubed? Well, we know that we would need a 12 and we would need an x squared. So we're going to write that up on top, and now what we're going to do is multiply that 12x squared across to both of these terms in our divisor. So make sure you distribute it across. So this would become 12x cubed, and minus 2 times 12x squared becomes minus 24x squared. Now in your long division algorithm in elementary school, remember what you did next. You wanted to subtract so that you could figure out what your remainder was. So that's what we're going to do here as well. We're going to draw our line and we're going to subtract. Now you could either subtract all of this using parentheses, or what I like to do is just distribute that negative in my head. So this would become minus plus. So you change all of your signs of that bottom row. So the 12x cubed was positive, now it's negative, and the 24 was negative, now it's positive. Now if you're doing this correctly, these first two terms should cancel out, and our remainder will be negative 5x squared plus a 24x squared, which is going to give me a 19x squared. And I haven't used these two terms yet, so I'm just going to carry those down, and then I'm going to do this all over again. So I'm going to say x times what would give me 19x squared? Well, I need a 19 and I need an x. And we're going to distribute that across to both the x and the 2. So 19x times x is 19x squared. 19x times a minus 2 is a negative 38x. Then you draw your line and you change your signs. So this would become minus and this would become plus. And now we're going to add down. These should cancel out. Negative 14 plus a 38 is a positive 24x. I still haven't used that plus 1 on the end, so I'm going to use that, or bring that down so I can use it one more time. And we're ready to do this one last time. As long as this degree here is the same degree as your divisor or higher, you can keep going. So since it's the same degree, this should be my last time that I'm going to do this. X times what would give me 24x? I need a 24. And then I'm going to distribute that 24 across, so I'd get a 24x, and a minus 2 times a 24 is a negative 48. Draw my line, and then I change my signs. So this becomes minus, this becomes plus. These two cancel out, and 1 and 48 gives me 49. So a couple of terminology here. This, as I've mentioned, is called your divisor. This is the original polynomial. Sometimes we'll call it p of x. This up here is called our quotient, and that's the result of doing our division. And then this number down here is called our remainder. So when we go to write out our final answer, your quotient is the majority of your final answer. So you're going to write that nice and big. But we had some remainder, so we want to add on our remainder. And notice I'm putting a plus sign after that 24 to add on my remainder. And it's a remainder fraction. So the number that is your remainder right here, that goes on top of your fraction. And what goes on the bottom should be your divisor, whatever you were dividing by originally. So this is going to be an x minus 2. So this is our final solution. Okay, let's try one more example. So here again we want to do long division. Now before you jump in, make sure that the polynomial that you're dividing into is in descending order and every term is accounted for. This one is not. I've got a fourth degree and then I jump down to a square, then I jump down to a constant. So I'm missing my cubic and I'm missing my x to the first. So this may not work out really well for me if I don't throw in those extra terms that I'm missing. So this is how you would want to rewrite this. So I am going to leave the x minus 1 where it is, but I'm going to put 3x to the fourth, and then next should be that x cubed, which I'm missing. So I still want to hold a place for it, but I don't want to add anything new to the original problem. So we're just going to put a coefficient of 0 in there so that we're really just adding a fancy 0. We're not changing the problem at all, but we are holding a place. We're making a placeholder column for any x cubed terms that we might need. Then the next lowest term would be the x squared, and then the next lowest term should be an x term, which I don't have, so I'm going to do the same thing. I'm going to add in a 0x. I'm not really adding anything, I'm just adding 0, which doesn't change the problem, but I am keeping a placeholder column for those x terms if I need them. And then we would have our constant on the end. So now we have every term accounted for and it's in descending order, so we're ready to go ahead and do our long division. So x times what would give me 3x to the fourth? I need a 3x cubed. Then we're going to take that 3x cubed times both of these. So 3x cubed times x is 3x to the fourth. 3x cubed times minus 1 would be minus 3x cubed. Draw my line, change my signs. So this becomes minus, this becomes plus. Now notice if I hadn't put that 0x cubed in there, then I probably would have lined up this 3x cubed term right under that x squared, and I wouldn't have been able to add those because they're not like terms. So by putting in that 0x cubed, it sort of helps prevent you from making a mistake and trying to add terms which really don't have the same powers. So this is just a nice way of keeping yourself organized and helping avoid some common mistakes. So these two cancel out. 0 plus 3x cubed is going to stay 3x cubed, and I haven't used these terms yet, so they are going to carry down. And now I do it again. So x times what would be 3x cubed? I need a 3x squared. So I'm going to multiply 3x squared times x, just 3x cubed, and 3x squared times minus 1 is a minus 3x squared. Draw my line, change my signs. So this becomes minus, this becomes plus. These two cancel out. A negative x squared plus a 3x squared gives me a positive 2x squared. And then I bring down my terms and I keep going. So x times what would give me 2x squared? I need a 2 and I need an x. So 2x times x is 2x squared. 2x times a minus 1 is a minus 2x. Draw my line, change my signs, and these cancel out. 0 plus a 2x is a 2x. And I still haven't used the 1 yet. And I'm finally down to a degree 1, and my divisor was degree 1, so this should be the last time I need to do this. X times what is 2x? I need a 2. 2 times x is 2x. 2 times minus 1 is minus 2. Draw my line, change my signs. These 2x's cancel out, and I'm left with a remainder of 3. So my final answer is this quotient, nice and big, plus a remainder fraction. The remainder itself, the 3, goes on top, and the divisor goes on the bottom. And here's my final answer. Now long division, as you can see, is pretty tedious. So what we're going to learn in or what we're going to review in this next step is synthetic division, which is exactly this same operation, these same exact steps, but synthetic division removes all the variables from the algorithm so that you're keeping track of just the coefficients, and you don't have quite as much writing because you're not having to write all these x's each time. So it's a nice, quick, compact way to divide. However, synthetic division only works if you are dividing by a linear factor. Your divisor has to be linear. If it's not, then you must use long division. So that's why we teach you long division, because sometimes synthetic division won't work if you were dividing by, say, a quadratic or a cubic factor. So there is a purpose for long division, but synthetic division is a nice handy shortcut if you're dividing by a linear factor. So here's how synthetic division works. What we're going to do is we're going to start with our polynomial, and again it needs to be in descending order and every power needs to be accounted for. If it's not, then you need to put in a 0 coefficient. Now synthetic division removes the variables from the problem, so we're going to just keep track of the coefficients of this polynomial, and we're going to write the coefficients across the top. So this would start off with our 12, and that's our x cubed term, then the minus 5, then the minus 14, and then the 1. So every term must be accounted for, or else you need to put in a 0. Then in this little box off to the side, we're going to write what we're trying to divide by. And we're not going to write this whole divisor. What we're actually going to do in this little box is write down where would this divisor factor equal to 0. So where does x minus 2 equal 0? And if you were to solve that, you would get positive 2. So we're going to put positive 2 in this little box. So one thing to remember is the number in this box should have the opposite sign of the number in the factor. Because up here I had a minus 2, but I'm using plus 2 over here. So now we're going to draw a horizontal line going across with a little space in between. And this is how the synthetic division algorithm goes. First thing you do is bring this first coefficient down unchanged. So I'm not going to do anything to that 12 yet. Anytime you have a number below the line, it's going to be multiplied by this 2. So 2 times 12 is 24, and that gets written in the middle. Then you're going to add down to get the new number below the line. So negative 5 plus 24 is 19. Then we're going to multiply again. So 2 times 19 is 38, and 38 minus 14 is 24. Multiply again. 24 times 2 is 48, and 1 plus 48 is 49. The number on the end, right here, will always be your remainder, and these numbers here will be the coefficients of the quotient. And it's up to you to realize what degree this quotient should be. Since we are taking an x cubed and dividing it by an x to the first, a linear factor, what would an x cubed divided by an x to the first be? It would be an x squared. It would be 1 degree less than what you started with. And that's always true with synthetic division. So whatever degree you divided into, your answer should be 1 degree less than that. So this would have to be starting off with an x squared, 1 degree less than that cube. Then this would go down to the x term, and then this 24 would be the constant. So our final answer is that 12x squared plus that 19x plus that 24. And since we had a remainder, we're going to add to this our remainder fraction, just like we did with long division. The remainder number goes on top, and what goes on the bottom should be this divisor that you were dividing by originally, the one with the x's still in it. So this will be x minus 2. And that is exactly the same answer that we got up here doing it with long division. Same solution. But this time we had a lot less work up here because we didn't have to keep track of all those x's. Okay, let's try one more example here. So here's our long division problem from before, and we're going to use synthetic division on it this time. Now before we do, we want to make sure that we write all the coefficients of our original polynomial across the top, and anytime we have a power missing, we want to use a 0 coefficient to hold its place. So 3x to the 4th, I'm going to put that 3 first. There's no cubic term, so I need a 0. The squared term has a coefficient of -1. There's no x term, so I need a coefficient of 0, and my constant was 1. And then in my little box, remember, it's wherever this divisor would equal to 0, and that would happen at +1. So I want to put in a +1 in that little box. Draw my line, and then here we go. Bring the 3 down unchanged, and then multiply. 3 times 1 is 3. Add down, multiply, add down, multiply, add down, multiply, add down. The number in the corner is your remainder, and then these are the coefficients of your quotient, and your quotient should be 1 degree less than what you started with. So if we started with an x to the 4th, then this should be an x cubed that I start with, and then 1 less than that would be x squared, then an x, and then this last 2 is your constant. So our answer is 3x cubed, whoops, sorry about that, 3x cubed plus 3x squared plus 2x plus 2 plus our remainder fraction, the 3 goes on the top, and the factor, or excuse me, the divisor that we were dividing by originally goes on the bottom. So here's our solution. Okay, so we've reviewed long division and synthetic division. Now we're going to get a little bit more formal, and we're going to talk about some terminology here as well. We're going to talk about the division algorithm, and we're going to summarize the results of any polynomial division. So if p of x is your original polynomial, and d of x is going to be our divisor, with that divisor not equaling to 0, then there have to exist unique polynomials q of x and r of x. Q of x is going to stand for our quotient, and r of x is going to stand for our remainder, such that p of x, the original polynomial, equals the divisor times the quotient plus the remainder. And that remainder will either be 0 or it will be of degree less than the degree of the divisor. So this is kind of a formal way of writing out what the division algorithm really means. So let's take a look at our last example. Remember, our original problem up here was 3x to the 4th minus x squared plus 1 divided by x minus 1, and we got our answer down here. So let's kind of redo that problem, labeling it in terms of all of these labels up here. So the original polynomial that we were dividing into was that 3x to the 4th minus x squared plus 1. And what we were dividing by, that divisor, that was that x minus 1. The q of x that they're referring to in this division algorithm, that's the quotient. So that would be this polynomial down here, not including the remainder at all. So this 3x cubed plus 3x squared plus 2x plus 2. And then the remainder, in the notation that we're using here, we want our remainder to be a polynomial, not a fraction. So our remainder is going to be just this remainder number, just the 3. Okay? So if we label all of our pieces in this way, let's show that this statement right here, that p of x equals d of x times q of x plus r of x, is really true. And maybe you'll understand once we do this how all the pieces sort of fit together. So the original polynomial, this p of x, that was this 3x to the 4th minus x squared plus 1. And what we're showing is that if you were to take that original divisor, which was x minus 1, and if you were to multiply it by your quotient and add back in the remainder, you should get back the original polynomial. So think about that for a moment. Let me go back up here to our long division problem. If I were to take this divisor times this quotient and add back in our remainder, we should get back the original polynomial. That's what we're trying to show, that this x minus 1 times this big cubic plus our little remainder should give us back the original function. So hopefully you can see that that should be true, and we're just going to verify it by actually multiplying out and seeing what we get. So let's multiply or distribute on the right hand side. First we're going to distribute our x's across, so we're going to get a 3x to the 4th plus a 3x cubed plus a 2x squared plus a 2x, and then we're going to distribute our negative 1 across. So we'll get a minus 3x cubed, a minus 3x squared, a minus 2x, and a minus 2, and then we have that little remainder on the side. So if we do this, I only have the 3x to the 4th term. My 3x cubed and minus 3x cubed cancel out. We have a 2x squared and a minus 3x squared, so those combine to a minus x squared. My 2x and minus 2x cancel out, and my minus 2 and my plus 3 give me plus 1. And that's exactly what my original polynomial was. So it does all work out. So really all this division algorithm is saying is your divisor times your quotient plus your remainder added back in should give you back the original problem. Now note in this division algorithm that if the divisor in the division algorithm is of the form x minus c, which it usually is, most of the time we're dividing by linear factors, then the remainder, remember up here it says the remainder has to be either 0 or degree less than the degree of the divisor. So if the divisor is of degree 1, then a degree less than that would have to make it a constant. So the division algorithm could be restated in the following way. Our original polynomial has to equal our divisor, which we're going to assume is a linear factor of the form x minus c. That divisor times our quotient is supposed to equal our remainder. And since the remainder is supposed to be 1 degree less than your divisor, and our divisor is degree 1, that means this has to be a constant, a remainder constant. So let's plug in c for x in this equation. So I'm going to plug in c here, here, and here. So p of c equals c minus c times q of c plus remainder. Well, c minus c goes to 0, and 0 times anything is still 0. So what this shows us is that the polynomial, the original polynomial with c plugged in, will always be the remainder. And this is called the remainder theorem, and it's a really useful theorem. It says that if your polynomial p of x is divided by x minus c, then the remainder is just the value of p of c. So let's put this into practice so you can see what we're talking about here. We have x to the 14th minus 3x to the 12th plus x to the 10th minus 4x plus 5, and we want to divide it by x minus 1. But all I want to know is what the remainder is. Now think about how you could do that. If we didn't know about this remainder theorem, then in order to find the remainder, you would have to either do long division or synthetic division on this problem. And we've got an x to the 14th going on here. So if you were going to do synthetic division, for example, you'd have to have a coefficient of 1 for your 14th degree term. There's no 13th degree, so you'd need a 0. And then your 12th degree, there's no 11th degree. Then your 10th, there's no 9th, 8th, 7th, 6th, 5, 4, 3, 2. Here's our 1, and here's our constant. And then we would divide all that by 1. So because this is such a high-powered polynomial, you'd have to do all of this. Now, not that that's impossible to do, but it's a little tedious because there's so many columns that you have to work through. So here's the benefit of this remainder theorem. Instead of doing all of that work, What the remainder theorem says is that the remainder is just going to be the value of this polynomial with 1 plugged in. And where does the 1 come from? It's wherever this divisor would equal to 0. That little number you would put in the box if you were doing synthetic division, it's that same number. So if I wanted to find the remainder, instead of doing that big long synthetic division problem or an even bigger, longer long division problem, I could just take 1 and plug in 1 into this original polynomial for all these x's. So according to my remainder theorem, the remainder is just going to be 1 to the 14th minus 3 times 1 to the 12th plus 1 to the 10th minus 4 times 1 plus 5. And that's just 1 minus 3 plus 1 minus 4 plus 5. And I'm going to get a negative 2 plus a 1 is a negative 1. Negative 1 and a negative 4 is a negative 5. Negative 5 plus 5 is 0. So after all that, my remainder will just be 0. And that's good news because that means x minus 1 divides into this polynomial evenly because we had no remainder. So sometimes using this remainder theorem can really save you a lot of time. Instead of doing a big, long division problem, all I have to do is plug in 1 into this polynomial and I'll know whether or not my divisor goes in evenly or not. So it's a real time saver. Okay, let's take a look at this next example. We're asked to use synthetic division to solve this division problem. So let's do that first. We've got this cubic polynomial. It's in descending order already. Every power is accounted for. So I'm just going to write my coefficients across the top. 1, negative 1, 5, negative 2. And I'm dividing by an x minus 2, so I need a plus 2 in my little box. And let's draw my line. The 1 comes down, multiply, 2 times 1 is 2, add down, multiply, add down, multiply, add down. What information do we get as a result of this? Well, we know that this here is our remainder, and by the remainder theorem, the remainder is supposed to equal your polynomial with this number here, 2, plugged in. So since I did my long division and I found out that my remainder was 12, then that means the value of this polynomial up here with 2 plugged in has to equal to 12. So again, options here. You can either plug it in and find your remainder that way, or you can do long division or synthetic division to find your remainder. But regardless of which way you do it, it's going to be the same as the value of just plugging in this number 2 into your original polynomial. So by doing this synthetic division, we discovered that the value of this polynomial at 2 must be 12. Now here's one more theorem that's also quite useful. It's called the factor theorem, and I've already mentioned it slightly. It says that if you plug in c into your polynomial and you get 0, that's only true if and only if x minus c is a factor of the original polynomial. So in other words, this x minus c would have to divide in evenly and give you a remainder of 0 in order for this to be true. So we are going to prove this. Okay, now we probably haven't done a whole lot of proofs, but we're going to try a proof here on this one. And this is an if and only if statement. So there's actually 2 directions involved. You have to prove that if p of c equals 0, then x minus c is a factor of the polynomial. Let me write that down. So if p of c equals 0, we have to show that x minus c is a factor of p of x. That's one direction. The other direction is going this way. So we have to assume if x minus c is a factor of p of x, then that implies P of C is 0. So we have to prove this direction and that direction as well, because this is an if and only if statement. So let's start with this first assumption. Let's assume that P of C equals to 0 and show that that implies that x minus c is a factor of the original polynomial. Now, the only place to really start here is with that division algorithm. So by the division algorithm, we know that P of x, by definition, is your divisor d of x times your quotient q of x plus your remainder r of x. And in this problem, what are we dividing by? We're dividing by x minus c. So my divisor is the factor x minus c. Now, if we were to know that P of C equals to 0, what does that tell us according to the remainder theorem? So P of C equals to 0 implies that P of C equals to the remainder by the remainder theorem. That's what we said earlier, that your remainder, when you do your division, is always equal to the value of P at C. And if P of C is 0, then that implies that your remainder has to be 0. So that forces this to go to 0, which means P of x must be x minus c times q of x, and there's no remainder being added on because we know the remainder is 0 by the remainder theorem. So look at what we're left with. We're left with the fact that P of x is x minus c times some q of x, and that is exactly the definition of x minus c being a factor of your polynomial. So this implies that x minus c is a factor of P of x. Because what does it mean to be a factor? It means that factor times maybe some other stuff multiplies back into the original. So if something is a factor, that means it multiplies together with other things to give you back your original. And that's what this statement right here is saying. X minus c times some other stuff gives you back P of x. So x minus c is one of the factors of P of x. So we've just shown that if you assume that your P of c is 0, then x minus c must be a factor. Okay, now we're going to do a similar type proof, but going in the other direction. So this time we're going to assume that x minus c is already a factor, and then show that that implies that P of c has to be 0. So if x minus c is a factor of P of x, that means that P of x must be x minus c times something else. And that something else I'm just going to call q of x. Okay, so that's the definition of being a factor of P of x, that x minus c times stuff is P of x. So what happens if I plug in c for x? So I'm going to plug in c here, and I'm going to plug in c here as well. Look at what happens. And we're plugging it in here as well. If you plug in c, c minus c goes to 0, so this whole side gives you P of c. And that's what we were trying to prove. So we just showed that if you assume that x minus c is a factor, then we get the conclusion that P of c must be 0. So we've just proven it in both directions. Okay? All right, the last couple of problems here. Is x minus 1 a factor of this 12th degree polynomial? And state any theorems that you are using. Now you have several options here. If something is a factor, that means it has to divide in evenly and give you a remainder of 0. So one option would be to do division, like synthetic division, and show that your remainder is 0. That would prove that x minus 1 is a factor because it goes in evenly. Now, doing synthetic division on a 12th degree polynomial is certainly doable, but it's probably not something you want to do because you'd have to have your 12th degree term, your 11th, 10th, 9th, 8th, 7th, 6th, all the way down to your constant. So kind of like that earlier problem, it's doable, but it would be tedious because you'd have so many terms to keep track of. So another option is to use some of our theorems that we know about, namely the remainder theorem and the factor theorem. So if we're dividing by x minus 1, then that means we're trying to look at what happens at positive 1, right? That would be the little number that we would put in our synthetic division box. So what I would suggest doing here is letting p of x be this 12th degree polynomial, and let's see what happens if I plug in 1 into that. So 1 to the 12th minus 3 times 1 to the 10th plus 5 times 1 to the 8th, and so on. And that's a little bit tedious, but not too bad because these are just 1s, right? So this would be 1 minus 3 plus 5 plus 2 minus 4 minus 1. So we'll get negative 2 plus 5 is negative 3. Negative 3 plus 2 is negative... Oops, hold on a second. I think I said something wrong there. So 1 minus 3 is negative 2. Negative 2 plus 5 is 3. 3 plus 2 is 5. 5 minus 4 is 1. 1 minus 1 is 0. So what we've just shown is that p of 1 equals to 0. Alright, what can we conclude as a result of p of 1 equaling 0? Let me back up here a little bit. Remember that factor theorem? If p of c equals to 0, then x minus c is a factor of your polynomial. That's exactly what the factor theorem says. So we could conclude, and we could say, therefore, by the factor theorem, make sure you are naming or claiming the theorem that you are using. By the factor theorem, x minus 1 must be a factor of p of x since p of 1 was equal to 0. Now you could have also used the remainder theorem here as well and done some other options, but the factor theorem here is the quickest way to just claim that something is a factor of something else. So that's why I used the factor theorem. Alright, just a reminder, for every 0 there has to be an associated factor. So let's find a polynomial function of degree 4 with zeros 3, negative 2, 0, and 1. So we're actually going in reverse. We already know what we want our zeros to be. What must the original polynomial function be? Well, if we have these 4 zeros that we want, then what factor must correspond to them? If 3 is a 0, then according to the factor theorem, x minus 3 must be the factor. If negative 2 is a 0, then by the factor theorem, x plus 2 must be the factor. If 0 is the 0, then x must be the factor. And if 1 is the 0, then x minus 1 must be the factor. So to get the polynomial of degree 4 that has all 4 of these zeros, we just multiply them all together and label it p of x. And this is degree 4 because I have x to the first, one here, one here, one here, and one here. That's degree 4. So there's my final solution. Alright, that concludes our lecture on dividing polynomials. Good luck!